So I'm going to speak about two projects. Thank you, Eva. About two projects where AI helped us to overcome difficulties that are brought to industry by growing needs for flexibility. The projects are quite different. The first deals with optimization of layouts of production lines in factories. And the second deals with reconfiguration of machines during changeovers and a replacement of the manual routine work by a virtual operator that uses the historical data to recommend the correct setup based on the former experience. So let's jump into the first success story. Actually, the project was conducted together with Škoda Auto, the Czech car manufacturer, and I was motivated by the growing difficulties of finding space for new production lines. The situation is even more difficult during the transformation of the car industry, because in traditional production you need to incorporate the new technologies for the hybrid car. So it's much more complicated than traditional cars, but you don't have space in traditional factories. This project was performed at the end of life cycle of one car, Rapid, when 1/3 of the production hall where the bodywork, where the body is constructed, was about to be replaced by new machinery for new car model. So the problem is defined as finding the optimal configuration of the facilities within a production plant, and it's optimized based on optimizing criteria. For example, the maximal utilization of the available space, or minimization of the sum of the transportation lines, so to minimize the need for the intralogistics operations. And it needs to be subjected to the non-overlapping restrictions, so we need to have some follow some rules how to organize the individual workstations. So in general, the facility layout problem is NP complete problem, so the complexity is exponential, and starting with some size, it's impossible to find the optimal solution. In such cases, we have good experience with heuristics or meta-heuristics approaches, for example, various types of local search or evolutionary algorithms. So and this is the way how we use evolutionary algorithms. So one input to that problem is a description of the hall that's available. So it's defined by the width and height. So it's a rectangular area. We define obstacles there, the gray part, communications, the light gray part, and the origin, the beginning of the coordinates. In a similar way, we define the dimensions and the parameters of workstation which we want to place to the hall. So we have the working area, the blue rectangle. We have the handling area, so area that needs to be free for logistic purposes or maintenance purposes. We define the pivot point, which is in the left up corner of the bounding rectangle. And we define orientation. We can rotate in 90-degree steps. We can rotate the workstation within the hall. It's not. It's part. The safety is part of the. It's part of the inner idea of the workstation. So each workstation has its own certification procedure. And then another safety is the width of the corridor, the communication path. So it's yeah. The robots are placed in this blue zone. This is area which we give the system integrator to design and realize the robotic production line. For example, line that produces doors. right doors, right front doors, for example. Mm-hmm.
I think the question is very well. Was the same question because it depends on the architecture of the production planning.
Yeah.
I think this is what we call us for classical factory.
Mm-hmm. Mm-hmm.
But if you go to industry 4.0, as we explained,
Yeah.
the robots bring the objects to the workstation. We have
Mm-hmm.
robots. We don't have cage.
Yeah.
The floor layout must be different.
Exactly.
Good anyway.
Yeah, yeah.
Maybe your technology, and I think this is what Regina.
Mm-hmm. Yeah. It is. Actually, what I didn't say at the beginning, the solution is a replacement for the traditional approach where the engineers use a large table and they have pieces of paper representing the shapes of various workstations, and they move it manually and try to find various setups. Okay. So we have the hall, we have a set of workstations, we have the optimization objectives and some non-overlapping constraints. So working area can be overlapped with working area of another workstation. It can be overlapped with handling area of another workstation. It can be overlapped with whole communications. And working or handling area do not overlap with whole obstacles. What can overlap are the manipulation areas of various workstations. This is quite important because this motivates the evolution algorithms to put next to each other the workstation and naturally creates paths in the zone. So it doesn't look in a scattered way after optimization, but the system is motivated to find direct lines because of this condition. So this is illustration for approach. So we have defined the production lines. We run iterative evolutionary optimization, and after a certain number of iterations, we have a final layout. Exactly. I will talk about that next slide. Yeah. So it's quite important to have an efficient way how to represent in chromosome the individuals in the population. We use indirect representation. In this indirect representation, each candidate solution is a priority list composed of triples, and the triple is always the ID of a workstation, how the workstation is rotated, and was the constructive heuristic, how we actually position the object into the plan. So we have two heuristics. The one is the first is that we try to squeeze the new workstation we want to place. We start with the first workstation from the priority list and place it to the bounding box. If we have space in the bounding box, the rectangular area here in red, we have a space for it, we place it in it. If it's not possible, we use heuristic H1 to extend it to the right, or heuristic to extend it to the bottom downwards, to the bottom area. This is part of the chromosome. This is encoded, this heuristic where we place it. The first objective is to maximize the continuous free area connected to one edge of the production hall. So have compact free area where we can, which we can use for another equipment. And the second criteria is the minimization of the intralogistics connections. We know how the processes follows each other, so we know which production line is connected to which, and we minimize the transportation cost for total intralogistics operations. So regarding the evolution algorithms, we use two-point crossover operator, mutations, tournament selections, and from that we generate a new generation of candidate solutions. because we have more criteria, more objective functions, we use approach that generates a Pareto front of non-dominated solutions. So we don't offer to the expert user only one solution, but a Pareto front from which he can choose what makes the best sense to the current application. So this is a solution that maximizes the free space. This is a solution that minimizes the connections. And there are extreme solutions from the Pareto front. So the user gets all the solutions. Because we don't cover all requirements on the layout organization, we run it in an iterative way. So we show the results to the end user, to the engineer. He can move with the workstations manually. He can fix, he can lock positions of certain. Actually, it was, and at the beginning we have the basic structure of the corridors. So and this is like a recommendation tool. Yeah. You are absolutely right. That's why it's necessary to have this interactive search where the safety expert can manipulate with it, with individual stations and create the evacuation corridors as based on the law requirements. This is to support the creativity, to show the potential approaches, new approaches, and show what's possible and what not. So it's design support tool. It's not generator of the final solution, and it's a tool which speed up the process, and it was developed for Škoda Auto. So if we don't have any questions to this, I will quickly go through the virtual operator topic we use in Lego. So very popular topic among my colleagues. Not in direct conflict. Yes, actually, because when you minimize the overlap, you create a compact sectors, but it depends on the shapes.
There are several heuristics for
Mm-hmm. Actually, we didn't try other heuristics, only this extension of the bounding box if we can't fit the workstation into it. Yeah. So in Lego, they are suffering from very different business strategy they have in these days comparing to 70s, from which the design of production lines come. So in 70s, they had small, medium, and large set, and it was perfectly fine. The creativity came from the users, but this strategy brought them almost to bankrupt around year 2000, and they had to change the range and the broadness of the product portfolio. So now they generate every year about 80%, replace 80% of their production portfolio by new sets. That's why also the overproduction grows quite steeply now. The average batch size decreases. It means that they need to do changeovers much more often. So the recalibration of the packing lines is it's not something that happens every third day, but every third hour now. And what does it mean? So this is how the packing process looks like. So it's composed of creation of prepacks, the plastic bags with the elements, and then the final pack where the plastic bags are put into paper boxes as we know it from stores. Here we focus on creation of the prepacks, where we count the exact number of individual elements for the prepack. It looks like that. So this is the typical production line, and it's composed of 36 vibration drums counting machines, as you can see on the right-hand side. So the counting machine automatically counts the preset number of elements. It uses vibrations, and it from an unorganized heap of elements creates a row that you can count. You need to tune it. It's a general machine, and you need to tune it for every type of an element. You set up there 21 parameters, various vibrations, various speeds, and it's quite demanding task because you have 36 counting machines, 21 parameters you can set up. So it's 750 parameters that you need to tune during a changeover. What we develop is a system that reads the data, the setup data from the counting machines, and stores in a knowledge base. So we remember the good, stable solutions set by the human operators. We know how it works on particular type of a counting machine and also on a particular instance of the counting machine for a specific element, and we also know the dimensions and the shape of the element, so we can use analogies to estimate how the setup will work for a similar element. So this is the problem. So we have 36 counting machines, and we need to set up the 21 parameters to achieve the best production speed. We use clustering algorithms because we don't have, it's a non-supervised approach, and we don't have the supervisor at the beginning. So we analyze the strategies that were used by the operators, a wide range of strategies. Some operators are more aggressive, so they use higher vibrations. Some are more relaxed. It's slower but more reliable. At the end, the performance is almost the same. So we compare, we identify the strategies by the clustering. So we find some typical strategies, and we select a typical representation from that cluster of the strategy. And we select in our approach that's deployed, we select 3 different clusters. We focus on compactness of the cluster. So the first is the cluster with the most elements. The biggest cluster. The second are the most compact, so the minimal mean standard error and the maximal number of elements with 0 standard deviation, so some typical configurations. Features, there are we use the 21 controllable strategies we use for cluster. We standardize it. Of course, there are various dimensions. So we have the standard dimensions. So then we need to do the inverse operation. When we identify the cluster, we need to convert it back to the units that are expected by the system. And yeah, so 21 features. No. We use all 21. And the system currently is up and running here in Kladno. It's in pilot phase locally here, and it's supposed to be rolled out to the rest of world during next year. And actually, the expected impact is that instead of having 2 operators at the prepack line, there will be only one that will inspect the system that works correctly, but no manual fine-tuning will be needed, except the situation when new elements are introduced. Then using the analogies and the similarities is something that doesn't work that well. So at least at the beginning, we need to teach the system by manual setup of the parameters. So thank you for attention. That's all from my side. I lost the ability to control the presentation. Eva warned me that it will come. I was quite lucky that it came at the end. So thank you.